activity. Bearing in mind today's notions of the makeup of brown dwarfs and gas giants, we may estimate the mass of WISE 0855-0714 at anything from 3 to 10 Jupiter masses. This rather falls short of starting a thermonuclear reaction, but quite enough to keep the heat effectively trapped inside the planet. Taking into account our knowledge about natural laws, we can predict what the conditions on the astronomical body's surface are like. For example, according to research by David John Stevenson from the University of California in the US, gas giants similar to Jupiter don't cool off instantly after receding from their star. Their thick hydrogen atmosphere is quite reliable thermal isolation, while the dense and hot nucleus made up of metallic hydrogen can keep the planet heated for a considerable time. Estimates show that the temperature of the lower strata of a hypothetical celestial object's atmosphere may be high enough for liquid water to be around. It is likely to be present in the atmosphere as giant clouds made up of tiniest droplets. These deductions agree with the results of mathematical modeling of WISE 0855-0714 carried out by a team of scientists from the University of Edinburgh. It showed that the most likely temperature value of the planet's surface is 250 Kelvin or 23 degrees Celsius below zero. The celestial body's atmosphere also has a comparatively warm layer around 100 kilometers thick, whose density fluctuates from 0.4 to 1.2 milligrams per cubic centimeter. It is comparable with the conditions on the Earth, and so it is thought that this environment should be favorable for potential organic life. Incidentally, a planet doesn't have to be a massive gas giant to avoid freezing in the cosmos. In 2020, a rogue planet candidate was detected using gravitational microlensing techniques. And here is the long designation it got. It is still awaiting confirmation of the rogue planet's status, and its parameters have been defined only generally so far. According to preliminary data, however, the object is comparable to the Earth in terms of its mass, and is anything from 30 to 180,000 light-years away. According to our current scientific notions, an object with a mass like that is not supposed to be a gas giant, and is more likely to be a rocky planet. This, in its turn, offers good grounds to believe that the object formed in the protoplanetary disk of a planetary system as the latter was forming. It may have been ejected from the system as a result of a cataclysm in space, or alternatively, under the influence of a larger neighbor. After that, it was left to its own devices, and so became a free-floating planet. What will happen to it next is predefined by a combination of several factors. Provided the object's atmosphere is sufficiently dense, it will be reliably thermally isolated. Potentially, a layer of ice on its surface could produce the same isolating effect. In addition, with the object's interior scorching hot, and with radioactive elements undergoing decay, most of the hypothetical ocean will remain in a liquid state. If the planet happened to have a moon, it may have retained it on ejection. If this is the case, tidal forces are likely to continue to deform and warm up the lithosphere. Theoretically, with any luck, primitive anaerobic life forms may have stayed around, although of course it would be next to impossible to discover their traces now. Most of the data about the rogue planets we know today were arrived at following mathematical modeling and complex calculations. It was possible to do these calculations thanks to the tiniest bits of information gleaned with the help of orbital and Earth-based telescopes. Even as I speak, a project is being worked on known as Cleopatra. Its main objective will be to search for free-floating planets and other objects in space with subsequent definition of their parameters. The project relies on something called microlensing. It is a phenomenon when a celestial body passes between a remote star and the observer on the Earth and briefly interferes with the light emitted by the remote star in the background. When observed from different angles, the moment of transition will be registered a fraction of a second sooner in one observatory than in another. Referred to as lensing parallax, this effect allows scientists to gauge the distance to a detected object, as well as its mass and dimensions. An interplanetary spacecraft is planned to be created within the project. It is supposed to blast off the surface of the Earth as soon as in 2025 alongside a mission to Mars, after which it will enter its own orbit around the Sun. The project will be aided by a specialized artificial intelligence component, whose mission will be to process and analyze collected information. The Cleopatra project will certainly delight us with a wealth of exciting and important information, so there is a lot to look forward to. What is to become of all those rogue worlds out there, drifting quite by themselves in the dark depths of the universe? In theory, an orphan planet may be captured by the gravitational field of a star and become part of its planetary system, but this chance is by all accounts minuscule. Most objects like that are destined to wander for billions of years through endless expanses of space, while slowly and inevitably cooling off. Eventually, they're to be swallowed up by black holes, or else destroyed as a result of a cataclysm in space, never to reveal their secrets to mankind.
Football watching. Better with Pepsi.
It goes without saying that to detect a celestial object that absorbs all light shed on it is a challenging task, to say the least. That is why there are not that many confirmed black hole candidates today. Still, mathematical modeling shows that their number in our galaxy may reach 100 million. This may seem an incredibly big number, but since there are 200 to 400 billion stars in the Milky Way, it makes us realize that in all these expanses, black holes are objects one doesn't come across that much. In one of our previous videos on the topic, we mentioned that a star, the progenitor of a black hole, has to have a mass of at least 18 to 20 solar masses. Only this will ensure a powerful enough supernova to compress the scorching hot core of the star to an exceptionally dense clump of material. After this has occurred, nothing will be able to stand up to the object's gravity force and escape beyond the boundaries of a conventional sphere predefined by the so-called Schwarzschild radius. What used to be a star transforms into a bizarre object with an inner makeup that would defy description by the physical laws we're familiar with. The object, referred to as A0620-00 or V616, is one of the black holes closest to our Earth that we know of. It lies 3,300 light-years away from our planet and forms part of a binary star in the constellation Monoceros. The other object in the system is an orange dwarf with a mass half that of the Sun. Every 7.75 hours it completes a full orbit around an invisible object of unknown nature. Estimates show the mass of this invisible object to be around 6.6 times that of the Sun. It is admittedly too much for a neutron star. This leads one to believe that the bizarre invisible object is more likely than not a black hole. In addition to getting deformed and elongated by the more massive neighbor's gravity, the orange dwarf is also getting stripped of the outer layers of stellar matter. Spiraling streams of scorching gas gradually flow to the black hole and form a bright accretion disk. It is thanks to this dazzling disk that the black hole was detected. There are at least several dozen stars in the environs of V616, some of which almost certainly have their own planetary systems. It is highly likely that in the future, one of these stars will get dangerously close to the black hole and as a result will be sucked in by the object's insane gravity. This unfortunate star will have no choice, and in this case, the same slow demise is eventually awaiting the black hole's new companion as that of its current one. The process of interaction of a black hole with other objects largely depends on their mass ratio. The smaller the distance between them, and the more massive the black hole, the stronger the influence of its tidal forces over its companion. The star may be deformed by them and get stretched towards the system's common mass center. They can also form channels that would carry stellar matter closer to the black hole, adding up to its accretion disk. If the tidal forces happen to be strong enough, they may well destroy the object that is being sucked in by turning it into a fiery ring. it is assumed that there may be planets orbiting a black hole, just as if it were a regular star. In contrast to a widespread opinion, black holes are actually not able to suck in all objects around them indiscriminately. From the point of view of gravitation, in astronomical terms, they behave just like any star with the same mass. That is why, incredibly though it may seem, a black hole may well have a stable planetary system. There are several ways for them to form. Firstly, new celestial objects may originate in a nebula of gas and dust that is formed after a supernova. Influenced by gravitation, they first form clumps of material that collide with each other and attract cosmic dust. As a result, they eventually turn into planets and satellites, as well as large numbers of small celestial objects, like asteroids and comets. The radiation of the black hole's accretion disk may be powerful enough to warm them, and even melt ice on their surfaces. Hypothetically, a planetary system like that could be favorable enough for life to originate and, with any luck, evolve. Secondly, when a black hole captures and destroys another planetary system, some of its objects may choose to take up stable orbital positions around their new host. Of course, this makeover would bring about dramatic changes on the celestial object's surfaces. Thus, an ice giant may transform into an ocean planet, and a gas giant may lose almost all of its hydrogen and turn into a Chthonian planet. Thirdly, space wanderers like rogue planets or interstellar asteroids may also be ensnared by the massive object's gravity. Even though systems like that have not yet been discovered in practice, there is no reason to suppose they are non-existent. If, on the other hand, a planet is too close to the system's center, and the black hole is massive enough, other factors come into play. A scorching hot stream of material forming the accretion disk will strip the celestial object of its atmosphere, and its friction will slow it down and pull it still closer to the black hole. Eventually, extremely powerful tidal forces will rip the planet to tiny shreds. The debris will be pulled into the accretion disk and gradually melt in the hot gas around. In the end, they will inevitably get swallowed up by the black hole and, in essence, become part of it. It is posited that there are three main types of black holes to be found in the universe that are different first and foremost in terms of their mass. The first type can be found in the center of most spiral galaxies. These are gargantuan black holes with masses reaching several billion solar masses. The density of matter in the central part of a galaxy is generally extremely high, which is the reason why there originate a big number of large and bright stars quite closely packed. As they rapidly burn out, they transform into black holes, which in their turn rapidly grow and often merge with each other. As a result, supermassive objects are born, which are surrounded with giant accretion disks made of scorching hot material. They illumine space so brightly that it makes them seen from billions of light years away, even if their galaxy is completely unobservable to us. These objects are known as quasars. The second type is much more widespread, but at the same time, black holes like these are not that easily detectable. Their masses are close to those of stars, and they form out of large stars at the end of the latter's life cycle. By devouring other celestial bodies and interstellar gas, these objects gradually gain in size and eventually turn into intermediate mass black holes. They can also merge together, which generates gravity waves that distort space many light years around. The third type is the hypothetical primary black holes. Their existence has been inferred from today's theory of universe's origins and evolution. Fluctuations in matter that filled space in its early stages of evolution may have been favorable for black holes of infinitely small size to originate. It should be mentioned that according to estimates, the smaller an object of this type, the faster it evaporates, and at the end of its life cycle it turns into a tremendously powerful electromagnetic impulse. Modeling shows that primary black holes with masses around 10 to the power of 12 kilograms are supposed to be flaring up sometime around now, but to date no such event has been registered yet. According to a certain hypothesis,